So moving on to the workflow, what we're gonna see today is how to input satellite and reference data from the repository that is everything is there already. How to pre-process this data to prepare them for reclassification and satellite-derived bathymetry in this context, and what we do here is to create a land mask to take out the spectral information from land, which can influence our processes. Make a sanglet correction because sanglet is um, uh, is always there, and it's very tricky to take it out. And I will speak more on that on the next slide. We will create a depth invariant index to treat the influence of the water column to the spectral reflectance that gets out of the water and to the sensor. And then we will talk about supervised classification and the accuracy assessment, and how to do a satellite-derived bathymetry with the random forest classifier through Google Earth Engine. But first, I will kindly ask you to check if you have access to the repository with all the data. And from that point, we can move on to the practicum. So here you can see the outline of the sections that we're gonna visit, and on the right there are also some links about the respectful checkpoints of each section. Section 1. So here I will jump to the checkpoint later. We first import and display the PlanetScope image, a single image from one date. And we also drew the polygons that will help us to mask the land, correct the sanglet, and also estimate the depth IV, from now on, the depth invariant index. What is crucial with the last one is that for the classification, the polygons have to be future collections with classes and specific values to help with the training of the classifier. But the polygons for the sanglet in orange here for the sand for the DIV are geometries, and we will talk about that the reasons later. So first things first, we do the land mask. Let's go actually to the Google Earth Engine to do directly to see what's going on here. So as you can see here, we first, let me also zoom a bit. We first put the image that we're gonna use, and also that's quite crucial point because most of the images in the clouds are stored in integer value in order to save some space, and that's a good tip for your cloud drivers and your assets. And here we can see how we visualize this image, the settings for the visual parameterization, and here we call the function to map and also to see. So for the land mask, what we did was to create the near difference water index, NDWI. With that index, we create an information that can be used, it's not visible here, that can be used by the random forest classifier and retrieve, identify only the water bodies and mask the land bodies. So the results for that will be that image right here. Let me take the initial one, where we extract only the region of interest, all the region of interest. You can zoom in to see if it worked properly. We have some errors here, but we could always put more points to that regions, either points or line. On lines will do that work, will do the work. Moving on, we have the sangling correction, and it's something quite crucial for the marine remote sensing field. So when we use satellite images for our processes, the golden apple that we need is this green line here, the water leaving gradients. This is the true information from the bottom of the water column that we want. However, due to physical conditions, there are also some other noise that influence the reflectances that get to the detector. One of these is this orange line here, the sun glint, which you can see here on the upper right. And actually, it's a phenomena that occurs when the sun goggle and the sensor are positioned in such a way that a mirror-like reflection of the water will be present, and that's hides some crucial information. So Headley and her team back at 2005 used a function, create a function, better put it, to treat with that issue. In that function, they saw the relationship between the near infrared values and the optical values. And let me find the specific part for that. And by taking the slope between the optical bands, the optical bands and the near infrared bands, here it will be B4 for all the bands, and then using the slope. So to get the slope for that, we first need to create a linear fit and then create a dictionary where we'll go to each output of the linear fit and ask specifically for the scale. The scale under a Google Earth Engine is the slope of this linear regression. The other product will be offset, which in math terms would be the bias of the linear fit. With that information in hand, the geometries that we used for the sun glint with the orange color here will be used here to identify to find out the minimum value of the near infrared bands. This information will later on be subtracted by the multiplication of the slope of the whole image with the near infrared. Under that spectrum, our sunglint should be resolved in a certain extent, as it's in an empirical method, and every case study is quite different. So we can check the initial image here, and we could also stretch a bit the parameterization to see where the phenomena is more present. For example, in this region, we can see this white, bit turbid, if I may say so, area, and this is mostly because of sun glint and the sky glint. So we want to okay, here are the polygons I used for the book. There were also some sun glint here, I presume, but we could always add more polygons to be sure to the sun glint areas. Because what is important here for the function to work is to find the minimum near infrared value to subtract it, and it must be a value from an area with not much sun glint. So here we are before the correction, where we can see the phenomena here, and here is after the correction. But again, every case study is different, so you might need to play around with the polygons and where to put them and if you need them or not. Back to the presentation. So next step will be the depth invariance estimation, depth invariance index estimation, and that happens that we need it actually because the water column, as I said in the beginning, can really influence the spectral reflectance from the benthos to the detector. For example, in several cases, sand in optically deep waters seems to have, if not the same, quite similar reflectance signature with seagrasses. So it's not very easy to understand the deep limits. For example, if we go back and forth in these slides, you can see the area here above Tavronidis. It's not, the seagrass areas are not very quite visible, but after the index, it's more, the boundaries are there, more discrete to see. And let's go to the code part. So here is the Sanglin correction function, and here will be the diff procedure. And that's starting from the top, we'll start with a kernel function, which function was created in order to smooth a bit the noise from the previous functions, like the landmask and the Sanglin correction functions. So a kernel here acts mostly as a low-pass filter to smooth down the noise. Then we'll move to another function, the make positive function, which it might not seem so, but it's quite crucial. Since we're going to use logarithms later on, I will show you later, we really need to make sure that all the values that we're gonna put in the function will be positive. Because if they are negative, we will find, you can find some mask patches in your region. And speaking for experience, uh, that's not gonna be easy to detect if you are not familiar with what's going on. Moving on the main star of the event, depth invariance index, where we start in the beginning by creating these variables in here in order to use them as labels for the outcomes, for the outcome of the process, and also as labels of the bands that we are going to use for the process. This for loop here aims to create the same function, which will be run 5 times, which is the number of all the bands, and it makes sure to run the same function for everything. We do that because we need to get the covariance between the bands, as according to Lysenko, which I cannot recall. I think Lysenko, his paper back in 1981, he spoke about the relationship between the relationship between the ratio of the bands and how they could be used to estimate the depth invariance index. Therefore, we'll start by estimating the covariance of the image log, which image log is again the image we used with every time it will choose new bands, a new band ratio. Then that's why the loop is here. And here also you can see the log phase, because we need to take the log of this image log and then later use it with a reduced region to get the covariance. The covariance between these ratios, as I spoke before, depending the diff sand geometries. To choose the diff, the important here for the diff sand geometries is not only to draw them above sandy patches, but also drew them in in diverse depths, not only shallow, not only deep. So with the covariance in place, we here is the right equation. I will not go through that. Very intense. You can check the paper for that. And with that in place, we create the depth invariance index with the expansion function, where we go simply take the image 1 and subtract image 2 by multiplying of course image 2 with a coefficient, which coefficient we get from here. And then we create an image cut to put the product of the function. And let me show you the results here. That's what I told you about the slide, but here the visual parameterization are better. So we can see more or less not here, I'm sorry. Here, we can see more or less the boundary of seagrasses, but in this image, we can see them in a more accurate way. And also see information like here on the on the east part, that which information was not there before. Moving on to the satellite-derived bathymetry with random forest. That is wrong. It seems that I put wrong titles. I'm so sorry for that. So I will change it to classification with random forest. That's what we're gonna see here. Let's go to the checkpoint that would start with the classification. Here we are. So start with the simple things first. We create a function to use the same function over and over in any image we might need. And inside that function, here we have the merge. I'm sorry. For the classifier to work, it needs a future collection with all the points from all the classes in order to be trained. To do so, we create this merged D, which stands for the merge collection of all the classes. And since we use future collection and not sant.merge hard t.merge posity, and we use future collections, we also need to use this flatten function. And here, to prepare the training process, we ask Google Fencing to sample these point regions from the image in order later then to identify, to do the AI part and see the relationship between the spectral reflectances and the spectral reflectances, above the points of our future collection of our reference data. Yes. So the classifier that we're gonna use here, it's not random forest, but we can make it random forest. So sorry for that. But then we will have to change the functions later on, so I will not go there. And here we have the parameters for the classifier. In this, I'm so sorry for that. I thought it was random forest, but it's not. So the function, sorry for that. The arguments for the libsvm will be here, where gamma and cost, again, it's one of these things that are empirical and need to be changed according to the case study. You know what? I will just do it random forest to save some time. And let me remind myself the right name. Random forest. Smile random forest. Yeah, I am. When I started coding with Google Earth Engine, it was not Smile, it was simple random forest. And where were we? Yeah, here. So for number of trees, let's go with 15. Let's keep it simple. That should work. Yeah, it worked. But we don't have the chance to see the difference between the overall accuracies. Okay, so random forest is a quite simple classifier. The main thing we need to decide is the number of the trees. We did it with 15. Let's go with 20 now. And after deciding about the classifier, we need to classify the image. After that, the product of that will be the classified image, exactly what you see here, with a little of visual parameterizations, but we will talk about that later. Now, a classification is nothing than just a simple image if we don't have an accuracy assessment, and that's what I'm going to present to you right now. So with merge T, we had our training collection. With merge V, we have our validation collection, which according to theory should always be from different sources to be more accurate and have a proper experiment. So with that in place, we use what do we have? The reduce region function to extract the areas that we will later on compare if they are classified properly or not. And with that in place, we call the error matrix to actual first, predictive first. Let's go to see what's going on here. The error matrix computes a 2D error matrix for a collection by comparing two columns of a collection, one containing the actual values and one containing the predicted values. Now, the predicted values, we have it through a merge V, and the actual values, sorry, the actual values are through a merge V, I'm sorry for that, and the predicted values are the accuracy column here. That's what we do here. So with that in place, and also by putting the names of the classes, we run the accuracy function to the classification error matrix that we created above. And by having an error matrix, we can also have the consumer accuracy. That's what we do here, and the production accuracy. Google Earth Engine is quite a platform to do so. Their functions are pretty simple to operate, and there is also always a forum there to have your question answered from a big pool of developers. With that in place, what we do here is to transform the classification error matrix to an array, and we do that just to make our lives easier to manipulate that in order to create this error matrix here you can see on the right on the console. Above that, you can also see the producer and the user accuracy of our classification and the overall accuracy. Here we can see the functions for proper treatment of the arrays in order to create the error matrix that I show you on the right. And here the error matrix is created based to the function that we mentioned earlier. And last but not least, we have the printout commands for the overall accuracy, the user accuracy, and the producer accuracy. And last but not least, we have the return function where we ask the function to return us just this classified image. So the output of calling this function will just be an image and not all the accuracy assessment, because the whole accuracy assessment process is taking place inside the function. Moving on, here we have the visualization parameters with minimum value 0 and max value 2. So in total, we have 3 values, which makes perfect sense since we have 3 classes. And here we also have the palette. And I would also like to take a moment to talk to you about Color Brewer, or I think that was the name, Color Brewer 2, which can be a quite useful tool for map creation, as it can show you a variety of choices depending the number of the classes you have, depending of the visualization you want, if you want a sequential visualization or a diverging or a qualitative one. And it's also so good that they also have this parameter here for colorblind safety, for colorblind people, I'm sorry, to have proper colors to use. I will close the parenthesis here, and we will move to the next checkpoint, which would be not supervised classification. Again, I'm sorry for that. would be a satellite derived bathymetry estimation with random forest. And let's move it here. Let's check the code. So first things first, in order to run a proper satellite derived bathymetry, we need a proper uh, training collection for. So in that case, we have this future collection of depth, which should be accessible by you through the assets that we shared. And what we do here is to create a random column inside the future collection, which later on this random column will help us, I think here's better, which later on this column will help us to differentiate the training data from the validation data. And again, as I thought during the classification, it's really important to have to have your training data to coming from a different source from your validation data. But in this case, since and because of the character of these lectures, we don't mind of that, but you really need to pay attention to that on a proper study or for your papers, hopefully. Here we can also see, we also visualize, can we see it? Yes, we can. We also see the location, sorry for that. The location of our training collection of our, yeah. So next step will be to vector to image, to make this vector, to change the format, sorry, from vector to raster. And why we do that is because in some cases, like here, where you go out to the sea with a boat and a proper instrument and you get values every I don't know how many meters Dimitris took these points, but because of that you will find a problem in a remote sensing study, because in one pixel you might have several depth points, which wouldn't help which wouldn't help with the training process. Therefore, we take if I'm not mistaken, yes, the minimum value. We go to each pixel and take the minimum value of the enclosed training data and put that value to the pixel, which later on will be used for the training. This is, yeah, vector to image function is what we call to do what I just described, and here we call this function to do it for our training data and for our validation data. And here we have the function for the bathymetry. Again, to create the training collection, we ask Google Earth Engine to sample the region in order to make the relations, in order to find the relationship in the background, as we discussed before. And here we call properly now the Smile random forest classifier with 15 trees. The main difference here and the classification that I showed you earlier beside the training points is what we do here, where after we classify, we go and change the set output mode to have the regression value. With that in place, the final product will have the proper depth values, and then again we rename it. Set output mode function. It's a function that also works for me for my PhD research, and we can change by default is the classification as we saw earlier, but here we use regression. We can also use it to have the probability or the multi-probability of each class, which could could be very helpful depending on your work. Yeah, last but not least, just to why you do that? Yeah, last but not least, we also create this variable here to use it later in this line of code, to use it for the accuracy assessment, which accuracy assessment in this kind of continuous distribution as a depth will be the root mean square error and the R-square error. So for the R-square error, we need a covariance matrix, which was created here in this line. And you can find the equation easily online. And then we have the deviation. I'm sorry. Yeah, to see the deviation, which later on, will be put in the power of 2. And here we have the results where we call the deviation as it was estimated here, and take the mean value of all the deviations from all the points, get the mean value of this and square it, and simply like that we have the root mean square error. The R square, the R square is what the R square needs the covariance matrix. Yeah, okay, I should write something here, a comment or something, maybe next time. And here the deviation is for the root mean square error, while for the R square we run a covariance matrix. And here we have the results. Let me rerun it again. And another hint for visualizing depth estimations and bathymetries will be the palette here, to always check your minimum values, your maximum values. And also a trick that we learned to the university is, if you want to give a perspective of depth in your image, you could use cold colors for regions that you want to give them a depth perspective. Oh, sorry. And warmer colors in areas that you want to give them the perspective that they are closer to the observer. But then again, all things are trial and error, and it's not so obvious here. So I will also change this one here. But yeah, what I really like in Google Earth Engine is that you can really play around with these things compared with local systems that they need time to run the processes. Okay, it's not so obvious as I hoped for, but that's a hint that you could use anytime. And with that in place, I think we are done. And